Yeah. So again, thank you, Eric, for the invitation and for this nice sedaDNA community or society. My name is Hussein. As Eric mentioned, I did my postdoc at Umeå University Chemistry Department between 2018 and 2019, which was supervised by Michael Holmbo. And we were working on the interaction between DNA and lake sediments and how the content of mineral and organic matter affected or affects DNA absorption. To start off, I think we can all agree that a sediment core is a really nice thing that is actually an archive we can use to look at contemporary and ancient species to reconstruct past communities, since DNA is well preserved in sediments once it is bound for tens, thousands, and even hundreds of thousands of years. And this interaction between DNA and minerals, homogeneous minerals, let's say clean or homogeneous systems, has been well identified in the literature for during the last maybe 10 years or so. So for example, how DNA interacts with different clay minerals, swelling, non-swelling minerals, how it is affected by different pHs, cation strength, pressure, and temperature. We have an idea about that. However, this interaction between DNA and real sediments, it's less known, because in real sediments, we don't have like clean, homogeneous systems. It's a mixture of organic matter, minerals, organomineral complexes. So we still have a lot of, let's say, vague notions in this regard. And despite all the advances in sedaDNA techniques and species determination and reconstructing past communities, there are still a lot of challenges. For example, I'm gonna just mention a few. Sometimes there's an inconsistency in taxa determination based on the proxy or the determination method, or according to the sampling method. For example, this Venn diagram shows that by using DNA, it didn't really have a match, or the number of species between these different proxies didn't really match. There is a lot of discrepancy, even with all the sensitivity of the DNA techniques. Another example is that DNA in sediments collected from different parts of the river showed different number of species. For example, the one sediment collected from the right showed higher number of species in comparison to the other two samples. Now, this opens a question like, what's the cause of this? Now, there's a lot of causes or what influences this variation or discrepancies, the taphonomy, technical issues. But I would say to a big extent, it is related to the geochemical properties of sediments, the mineral and organic fraction, and what this sorbing material, the sediments, really is. We have to understand this material. So in my postdoc, we worked on the DNA absorption onto sediments and how it is affected by the mineral composition, the organic composition, the sediment sizes, and the aggregates, the mineral and organomineral aggregates. And we were later interested in seeing, can we detect a DNA hotspot within the heterogeneous material? DNA hotspot meaning that a part within the sediment which has a higher probability of finding DNA. So it is a DNA-rich zone within the bulk heterogeneous sample, in which we can save money, time, get reliable, and most importantly, get reliable results. And we were also interested in seeing if we can detect an infrared fingerprint of the DNA once bound to heterogeneous sediments. Now, this in fact is the second part of the project. The first part of the project is we have to understand the system, the sediments. So to know what the sediments are made of, from in terms of chemical composition, mineralogy, clay minerals, organic composition, the aggregates. And this gave us actually an opportunity to see how sediments changed post-glaciation in a Swedish lake. In this presentation, I'm just going to focus a little bit about the composition of the sediments because it is important, but also on the DNA hotspot. So in this study, a sediment core was collected from Sweden, west central Sweden, Hutagen. Our colleagues from ENG collected a 230 centimeter sediment core. And then they collected a bulk sediment every 5 centimeters throughout the core. And we took this bulk sample. We took an aliquot of each bulk sample throughout the core and further divided it into different size fractions. Now, the purpose of dividing it further was just to divide the heterogeneous sediments into smaller elements so that we have a better idea about their composition. And then to realize our first objectives, we determined the mineralogy by X-ray diffraction, determined the organic composition, chemical fingerprints, and the sediments were also dated, in addition to the determination of aggregate and sediment size by laser diffraction. After all of this is known, and we know the composition, then we go to the DNA absorption experiments to see how DNA is absorbed onto these fractions and sediments. So what we did is DNA absorption experiments onto bulk and the size fractionated samples. We did it by absorbing experiment using a specific mass of sediment. And we added salmon sperm DNA interest buffer at a specific pH, and we followed the absorption by UV. So we determined DNA concentration by ultraviolet. Additionally, we were also interested in seeing how organic matter affects DNA absorption. So what we did is we removed the sedimentary organic matter from the same sediments, the bulk and fractionated sediments, and we followed DNA absorption onto it. We also followed the changes by infrared, which I do not think is really interesting for the people in the sedaDNA-society, so I will not focus on that. So just to give a little bit of introduction or about the initial material used, the geochemical characteristics of the flake sediments, the first part. Even at the bulk scale, we can see that the sediments at different, let me see if I can pointer, yes, I think that would be better. So even sediment at different depth, they have different colors. So this is an indication that we have different composition, maybe different units within the sediments. And this is actually a bit, it's a really old sediment core dated back to 10,000 years. So it is expected to have this kind of variation. If we looked at the sediment aggregate or particle size, we can also see a variation. So first, let's look at the particle sizes for the sonicated sample. This is actually the particle size, not the aggregate size. And we see here that they have similar characteristics, the spectra in red, for the samples between 0 and 180 centimeter. Going further down the sediment core, we see a variation, a shift towards the left, towards smaller particle sizes here. This indicates that we might have roughly 2 units. The first unit, which is mainly in the first 180 centimeter, and then the second unit, which shows more variation. However, another type of variation that we see here is the difference between the black and red spectra. Simply put, it is the difference between the aggregates, non-syndicated samples, so it's the aggregate size, and the particle size. Here we see a big difference for the first unit. This difference is smaller for the units below, or for the sediments below, for unit 2. And this indicates that we have more aggregates in the first unit in comparison to the second unit. It's important to note that we have aggregates and they differ through depth, which we will later on talk about when I talk about the DNA absorption. When it comes to mineralogy, the same minerals were detected throughout the core, which are clay minerals, chlorite and mica. Now these minerals, they really absorb DNA, or they are preferential DNA binding sites. not like quartz, feldspars, and amphibores. They do absorb DNA, but to a lower extent. We can also see from infrared that the organic matter changed throughout the depth, which here is shown as different color sediment or spectra. But what I want to show in general is that throughout the sediment core, there is a variation of depth in terms of organic matter and mineralogy, mainly clay minerals and the other minerals. Well, this was the bulk fraction. When it comes to the fine fraction, we can also see a variation. For example, mica, again a clay mineral, which absorbs DNA, is mainly found in the fine fraction, whereas quartz and albite, they are mainly found in the coarse fraction throughout the sediment core. Fine fraction had more amorphous material, amorphous minerals, but had lower organic matter. So, as we saw a variation of the mineral and organic composition with depth, we can also see variation as a function of sediment size. And this, although not really related to this study, but from this mineral and organic variation or evolution, we can mark the pre-glaciation period, the early Holocene or deglaciation period, where the ecosystem started to form by increasing organic matter and clay minerals in the system, and then the Holocene, when the watershed became more mature. So what I want to end with in this part is, in this 230 centimeter sediment core, the sedimentary composition varied as a function of depth and as a function of fraction. And now to the second part, how does it affect, or does it affect DNA absorption? Because if you have a 230 centimeter sediment core with this different composition as function of depth and size, let's see how it affects DNA absorption. So we focused on the geochemical identification of potential DNA hotspots in lake sediments, which was published last year. Again, we had bulk and size fractionated sediments. We added salmon sperm DNA, and we saw the amount of DNA that can be absorbed. I'm going to give here an example about the fine fraction, the fraction below 4 micron, and the really coarse fraction. What we first see here is that in the U1 sediments, in the first unit, there is a higher DNA absorption capacity in comparison to the lower sediments in U2, which was the case of both size fractions. Moreover, the DNA that was absorbed onto the fine fraction here is more than the coarse fraction, as we see here from the x-axis. And this is mainly related to the higher content of clay minerals, again, the DNA, which absorb DNA, in the fine fraction. So we can agree that clay mineral has a role even in heterogeneous sediments. It has a role on DNA binding. However, we did the same experiment after removing the sedimentary organic material, just to check what the sedimentary organic material plays in DNA absorption. And you can follow it in the red parts. It's usually DNA absorption decreased in most sediments, especially in U1. How we can describe it is, I'm going to give a little schema here, which shows a mineral with some organic matter. So this is, let's consider it a simple organomineral complex. And DNA can bind to the organic part and to the mineral part. However, after we remove the organic matter, we don't have organic matter anymore. DNA can only absorb onto the mineral part. Therefore, DNA absorption decreased, as we see in most cases. But I forgot to mention, every point in this figure represents a triplicate, and the standard deviation, which is not really seen, but sometimes it's seen like here and here, it is a standard deviation of these triplicates. So even with this, you might see it as a small variation. It is actually a variation. However, in a few layers, like here, the sediments that did not contain sedimentary organic matter had higher absorption capacity than the initial sediment. And this, again, in a simplified schema, can be shown that this is an organo-mineral complex, and DNA can bind again to the mineral and organic parts. After removing organic matter, the aggregate might break, disaggregate, and then more surface area is available for DNA binding. Thus, more DNA can bind after organic matter removal. So here we have different cases giving different results, opposing results, in fact. And what actually happens in the sediments is not one without the other. It's actually both of them happening probably at the same time. It's a heterogeneous system, and this is how it works. But how organic matter affects DNA absorption, either by increasing it or decreasing it, depends mainly on the aggregate type and the mineral and organic composition. Going back to the clays, okay, clay is well correlated to the amount of DNA that can be absorbed onto these sediments. The correlation here is a bit lower for the initial sediments in comparison to the sediments after organic matter removal. Again, this better correlation comes from the fact that after removing organic matter, some of the organo-mineral complexes are disaggregated, meaning more surface area is available. But how fair is it to include the sum of clays? In our systems, we had clay, we had chlorite and mica. And even though it is a nice correlation, is it fair to combine clay minerals together? So we constructed a principal component analysis plot in which we show the correlation between the different parameters in different sizes here in these different shapes. So for example, mica in yellow is always correlated to DNA, regardless of sediment size. So it's not a straight correlation with DNA content. But chloride here was oppositely related to DNA in the smaller fractions, in the 0.4 and 416 micrometer fractions. Again, we go back to the aggregates. And indeed, as we've seen previously, but I didn't highlight on it, that mica was really distinguishable between the fine fractions here and the coarser fractions. So there is less mica in the aggregates. When it comes to chloride, this distinction between the different size fractions was not so obvious, probably because mica, even though it absorbs DNA, the binding sites of chloride were not available, thus showing this opposite correlation. So from what we know so far with the correlation between different minerals, is it possible to determine a DNA hotspot? Or to actually to do some kind of simple modeling to determine where the sediments are most likely to be found? We can see it by the multiple linear regression model using mica and chloride as explanatory variables, and we can see that the DNA, theoretically absorbed DNA, fits within the experimental DNA that was absorbed onto the sediments. If we used more variables, like feldspar and quartz, which do not really absorb that much DNA, but still do, the correlation is even better. However, if we added organic matter to the equation, then here we see like a big jump in a better correlation. And if you add all the minerals and organic matter, we see here a clear correlation between the experimental DNA and the theoretical DNA. This means that if we know the mineral and organic composition of our matrices, the sediments, we can expect where to find DNA. We can know where the DNA, or expect where the DNA hotspot is. So in conclusion, the mineral, the organic fractions of the sediments, the aggregates, they play important roles in DNA binding. And knowing the composition of the sediment makes it easier to estimate or to determine a sedimentary DNA hotspot. And by focus sampling on such hotspots, maybe this will help in obtaining less inconsistencies between different methods, having more reliable results in reconstructing past communities, and maybe, as Eric mentioned at the beginning, like to know where some species or taxa are, where DNA is. So I leave it to the sedaDNA-society to do some kind of, I hope that they can do this kind of test. Our experiments were done on salmon sperm DNA, not on sedimentary ancient DNA, which would be too low for our experiments. But I would be interested, I think I cannot assume everybody would be interested, but I think it would be interesting to see if different fractions were collected from the same sample, from the same bulk sample, like a really small fraction and a coarse fraction or a bulk fraction. And then DNA was determined. Would we see the same taxa? Would we see the same species? Do they intersect? Or would we see more discrepancies? Like, this is something that I really would like to see in the future. And this is it for me. Thank you.
Thank you very much, Hussein. I really like this presentation, and I think your question at the end is, yes, we need to know more about that. Many experts here will probably say the same than me. So I will leave the room open for questions if you have some. And you can put your name in the chat, for instance. Before that, I would like to ask you, Hussein, if you're looking for a job or if you found a position somewhere.
Yes, indeed. I finished my contract last year, and at the end of last year, and I'm still looking for a position.
Okay, so maybe it's a good place to say it. You may have people around that would be interested to have this kind of skill in their lab. I mean, if I had a lab, I would be very interested.
Oh,
okay, Rosie raised her hand.
Oh, thank you very much, Hussein. That was a really interesting discussion. And actually, your work has formed a lot of my discussion that I'm currently writing up for my PhD. So I'm looking at sedimentary DNA within non-lacustrine paleo-environmental depositional environments. And one of the things I'm really interested in is, so I have my results and I have quite expected sort of outputs for these sort of fluvial environments. So I have compared to like paleo ecology sort of standard practices. So looking at like pollen, for example, you know, my fluvial sands are pretty much devoid of any preserved DNA. And then I'm looking at environments where paludification is sort of allowed for peat formation before sort of inundation of the environment. And I have this really nice interface between sort of the final sort of clastic fluvial deposits prior to peat formation. And I have this one sample that has a really high output of preserved ancient DNA that sort of relates to the environment in terms of sort of floral diversity and things like that. And I was just wondering how you would test that in a lab. So a lot of my discussion at the moment is hypothetical, looking at paludification and, you know, the reduction in sort of oxidative processes, sort of that sort of aspect of taphonomy for sedimentary DNA preservation. But I was just wondering how you would test something like that in a lab setting.
Interesting question. Like I would say, if I understand correctly, you have some, let's say, active minerals or like a lot of changes that can occur to the mineral. So in that case, DNA might be degraded, might absorb and desorb, or you can, which might explain why you cannot find DNA. All DNA is more absorbed in the organic and the clay part, which cannot be easily extracted. What I would say is, if you can work on a selected part of this samples, like I don't know really what your sediments are made of, But if you can focus on a part of it, if you have coarse fractions, just eliminate the coarse fractions, don't work on them. Maybe you can work on the finer fractions, the clay particles, or maybe organic rich material. But in that case, you need to, I cannot say make sure, because I suppose it's hard dealing with that kind of material. You have to try to disaggregate the sample, try to make the DNA that you have in your samples, make them maybe more exposed, so that when you extract the DNA, they can be extracted instead of being, let's say, well within the aggregates.
Okay, brilliant. That's great, thank you.
Also, one note about the oxidation reduction. So it depends if your system is rich in iron. And from what I know, I haven't worked with this kind of material with DNA, but from other studies and something that I worked with before, iron-rich samples, and if you have a change in the oxidation, that might be really difficult because once released, the DNA, if you're extracting DNA, iron oxyhydroxides, for example, they can easily reabsorb these released fragments. So what I would do, I don't know, I try to fix the system, try to have it in a fixed state in terms of redox or pH, so that you maybe limit a bit of unexpected or unwanted changes.
Oh, brilliant. Okay, thanks very much. I'll have a think about it.
We have a question from Elena, and after Camille, and after Tony. Sorry, I will try to keep it in the order. Elena, please.
Hi, really cool talk. I really enjoyed it. It's something that I thought about a lot in the beginning of my PhD, and I tried to look at some of these questions, but unfortunately I don't have access to an XRD and everything like you do. And so I was working with Pleistocene sediments, and so I did try size fractionation where I use much bigger sizes. So I had been talking with someone who does OSL dating and had worked with them to try and just pick size fractions, and perhaps I was quite naive about this. And so I used 1 millimeter and then half, so 500 microns, and then going down to, I'm trying to pull it up because this was 2 years ago, like 250 microns, and then my smallest cutoff was 40. So this is above kind of what you had looked at. And when I did this, I saw no difference in terms of the preservation. So the amount of ancient DNA I recovered across the different size fractions, as well as the taxa that I recovered across all of the different size fractions. But I'm wondering if it's because I'm looking at too large of particles. Do you think it's something that would be worthwhile to, I guess as a side note, also I did FTIR on each of these size fractions to see if I saw any differences, as well as looked at these fractions under a microscope. And they all looked the same, just smaller and smaller versions of the exact same components. Yeah, I'm curious if you would recommend looking at smaller size fractions.
Can I ask you how you did the size separation?
Sieving, wet sieving.
Wet sieving.
Yeah.
Okay. Yeah. What I would say, so you didn't find any variation, and it's not really easy to come with a common method for different sediments. Some sediments, they have more aggregates, and even if you look at the fraction, so maybe the smallest one was 40 micron. And if we want to compare it to the clay fraction or clay minerals, let's call clay minerals, those are usually in the fraction below 4 micron. So it's the really small, like 4 instead of 40 micron. In your case, I would say in this kind of sediments, you have a lot of aggregates. So it's not really easy to see the variation in the sedimentary components, especially at these big sizes. even with infrared, it might be used to see some kind of variation, mainly in the SIO stretching peak, the positioning, some of the octahedral OH groups of some clay minerals at regions around 3600 centimeter -1. But it's not really the best technique to see the composition of the sediments. I would say you don't have an XRD, but XRD would really make things easier for you. If you still have the sediments, I would suggest just for the 40 micron sediments, you can do some kind of wet sieving in the, or if it's too late, maybe you can do some kind of settling experiment in clean conditions in which you can set according to Stokes law, which you can find in the literature online. You do not necessarily get the particle sizes, but you can separate bigger fractions from smaller ones. So why 4 micrometer is important? Because this is the limit between clay minerals and the other fractions. I would say, hopefully, if you look at these smaller fractions, I cannot assume anything, but I would say there's a big chance that you will get more variation between the different fractions. But again, to be sure about that, you have to look at the mineral organic composition of the different size fractions, because the size of the aggregates, it differs a lot between different systems, really.
Okay, cool. Thanks so much.
Okay, so we have a question from Camille, and after Tony, and after Rui, and after Hideyuki. So please try to have concise question. You're mute, Camille.
Okay, thank you, Eric. I will do my best. I actually have tons of comments and questions, but I will write them in an email to Hussein. Thank you very much for your presentation, Hussein. So I see that there are ways of getting these DNA fractions, as you say, but how much do you think of the total DNA we want to look at is being lost in all these processes that we should use separating the DNA, separating the particles in sizes, moving them from one place to another? I know, for example, I work on prokaryotic DNA, and I would be so afraid of contaminating my samples if I add more steps between the moment of sampling and extracting the DNA.
It's an interesting question. I think we have to be more specific about what DNA. If we're looking at DNA that is preserved or that has been absorbed by minerals, mainly clay minerals, I'm not sure, but they have been stored for a long period of time, and to dissolve that, you might need either some kind of enzyme or something to break the bond, or something to replace the DNA that is absorbed onto the clay minerals, mainly clay minerals, but minerals or sediments in general. So if you're looking at bound DNA, you can use a system or a solution where you do your size separation. It doesn't have to contain anything, so that there is no competition between the components, cations or other things, and the DNA. But if you're looking for something that is not absorbed, then yes, they can be easily released from the sediments, or you can easily lose them. They might be even degraded, either by the bacteria inside your system, by light. I would say in that condition, you have to be really careful to have your own system in which you are sure doesn't contain any enzymes or something that can break your DNA.
Okay. And
No.
Yeah, okay, go ahead. No, Eric, it's okay. I will ask questions later.
So we will take the three. We'll take the three next question, and after we'll stop question and start discussing something else, if it's okay for all of you. Sorry, Camille, you can send an email to Hussein. Tony?
Okay, very good. It's very interesting, Hussein. It's a quick question. How did you remove your organic matter? Because it is very difficult to remove organic matter without changing the fundamental nature of the aggregates and, of course, the relationship of particles to each other. It's basically removing organic matter is, yeah. How did you do it?
Yeah.
Sort of.
That's an interesting question. I didn't mention it. I briefly mentioned it, but maybe not. This is really important because what we wanted to do while removing the sedimentary organic matter is not to modify the chemical or the mineral composition of the sediments. With the aggregate size, obviously it varies. It will change. This is something that we know and we didn't really focus on. But we used a gentle chemical method using sodium hypochlorite, NaOCl. Now, in this method, you don't necessarily remove all organic matter.
Yeah.
From our test, it was, I would say, more than 90% of organic matter was removed. But this is just to ensure that we do minimal changes to the mineral composition of the sediments. So this is some kind of gentle organic matter removal.
Yeah, no, I understand that. That makes it much more sense. Yeah, thank you very much. Yeah.
My pleasure.
Thank you. So it's actually the same question, or almost the same question than Rui. I wonder, how do you remove organic matter without destroying DNA? Yeah, you can say something, Hussein.
Yeah, so in our case, DNA is destroyed. So that's no doubt. Using this method destroys DNA. So if you're looking at sedimentary ancient DNA, you cannot remove organic matter. That would be a big no. Whatever method you use, that will not be used. What you can do is maybe to shake it, to disaggregate it by some kind of gentle force, not sonication, not chemical treatment, just to preserve the DNA. But this is what we did, this kind of experiment, just to see what sedimentary organic matter has a role in DNA absorption onto the salmon sperm DNA, which we introduced.
Okay, cool. And the last question is from Eduyuki Doi from Japan. And I think I have the answer to this question, what kind of DNA extraction kit you are using. And maybe it's pore soil, like most of us.
For me, I used sediment. I used salmon sperm DNA. So
the DNA extraction protocol you used?
I didn't extract it. The experiment was DNA absorption experiment. I added a known DNA concentration into the sediments, onto the suspension sediment with DNA containing solution. And then I quantified the DNA remaining in the solution. And that way we can calculate how much DNA was absorbed onto the sediment. But I tried a DNA extraction just to make sure that we're in the right way. I think it was the thing that you used, Eric, with
yeah, it was pore soil then.
With Frederick. So I used this just to make sure that we have this amount of DNA absorbed.
Yeah, exactly. I remember that. Yeah. Cool.